The following is a conversation with Dr. Michael Robinson, mathematician, statistician, and professor at American University. We are discussing his absolutely amazing discovery about large language models, how you can literally hack them to retrieve the embeddings of the tokens they were trained upon. My name is Dr. Krzysztof Piotrowski, and I'm the host of Unorthodox Views. If you like the podcast, please share, press the like button, subscribe, and if you really enjoy it, there is a Patreon link in the description. Hello, Michael. Thank you very much for coming to the podcast. I am super excited about to discuss your research because it has tremendous consequences for large language models. I think it will be surprising for everybody. I wonder if anybody knows about it. So specialists in LLM should be really interested in this talks and in general AI people. Okay, so let's start from the beginning. You just published an arxiv two papers, which have very interesting claims. Maybe we can go over them in starting with basics. So
sure, absolutely. Right. So first of all, thank you for inviting me here. This is interesting and an interesting time in AI. And so one of the things that kind of motivated these papers, if I can before I dive into it a little bit, is there are assumptions that are made when people build any kind of engineered system. There are assumptions that go into, for instance, what my voice is going to sound like. That drives the microphone's design. So if I'm going to build a large language model, there are assumptions about language that go into that model. And so what these two papers are about is testing some of those assumptions and testing them really at a fundamental level. So the two papers that are testing some of the assumptions that go into the basics of machine learning, which in the original context of what machine learning is for, it's a generalized form of regression, makes sense. Those assumptions are valid. So the question is, do they really hold when we talk about language? So the first paper is, does the set of words or fragments of words, tokens, does that lie on some kind of nice smooth space or a manifold? And really it's the picture I want you to have in your mind is that of sentiment analysis. The idea that some words have an emotional valence to them. Some words are positive, happy, wonderful, excellent. Some words are not so positive, corruption, pain, wounds, injury, sickness. And so you can imagine you put them on a sliding scale. The more positive words get a positive number scale. The words that are negative get a negative number scale, and the words that are sort of not either way are kind of somewhere in the middle. So you put numbers on them. And what people have found is that if you tag words this way, you could say, oh, I've got a text and I'd like to slide it a little more positive. Well, you can substitute the words that are a little more on the low end of that scale for words that are a little higher in the scale. Make it a little more positive, kind of dredge it up. Or, you could dredge them down just the same way. So that sort of begs the question, are there other axes besides emotional valence that I can have? Can I put a whole bunch of numbers on each word or each fragment of a word? Maybe we break the words down to their stems. We're speaking in English right now. English conjugates verbs, doesn't decline nouns. But for instance, run and running and ran are all really instances of the same verb. So maybe we tag to run with a bunch of coordinates. The question is, well, can I do the same kind of thing I can do in sentiment analysis? Push the words around a little bit, smoothly move them around. And if you can, that should be a space that is called a manifold. So the question is, does the space of words, tokens, look like a manifold or not? It either is or it isn't, and that's actually a mathematically testable thing. And it's even statistically testable. We get a p-value. What's the likelihood that this kind of thing is true? So that's what this paper is about.
Yeah, so manifold, just for people who don't know the definition, would be a multidimensional space which is Euclidean or flat locally.
It looks like Euclidean space locally. And actually kind of important technically in both of these papers is that it has the ability to express local changes. So you need those two axioms. Every point, if you look around that point, look at a neighborhood of that point, So look at words that are nearby, perhaps. That looks like multidimensional Euclidean space, Rn or something like that. Okay. And additionally, I have the ability to make a small local change to functions in that space. If I could do that, I have a manifold.
And that has been an assumption of machine learning forever.
Forever, and for good reason. For a good reason. It's totally reasonable. If I'm trying to fit, say, for instance, I want to model the properties of plants in order to classify them into genus and species. Very reasonable to do that, because the length of petals and the color spectrum on each of the different leaves, those are numerical in some sense, those are quantitative. So the real, I guess you will, the real assumption underlying large language models could well be expressed as saying, I think words actually are numeric. And as a statistician, that kind of makes my skin crawl a little bit. And so I wanted to go find out, is that true? So that's the first paper. The second paper is, okay, if my words really do lie in some kind of space, manifold or not, well, they've been given coordinates. Those coordinates tend to be hidden from the user. If you go put in a query, talk with ChatGPT, do you see the coordinates associated with each of the words that you've typed in? No, of course you don't. They're hidden deep inside the bowels of the model. And the real question is, okay, my first paper said I can test whether or not those points all lie on this multidimensional manifold or not, or whether or not there is a manifold that they could be reasonably thought to lie on. Okay, fine, but in order to do that, I need to know the coordinates, which would ostensibly say someone like OpenAI could hold back that proprietary data, and we wouldn't be able to test their model for them if they didn't want to. The second paper puts limits, mathematical bounds on how much they can hold that information back and how much that structural information necessarily shows up in the output. And if it shows up in the output in a controlled way, we can start to peel it out by carefully structuring queries. They're not like, hey, ChatGPT. They're not semantically meaningful. They look more like writing malware, actually. The way that you build a malware exploit is by poking at the electrical nature of the circuit. We're doing the same kind of thing for a large language model. And if you do it in the right way, you can get that structure.
Which is absolutely amazing and has tremendous consequences, which we will go there, so stay with us. But this is very technical, but very interesting how to get there. But let's go back to the first paper first, to discover this amazing thing, right? So the assumption, as far as I understand, was that the embeddings create locally Euclidean flat spaces. Not only that, which is a manifold, but also the manifold is less dimensional than the embedding. So let's say you have an embedding of few thousand dimensions, but actually you could run something like PCA, principal component analysis, and reduce the number of dimensions to have like even more compressed version, let's say, right? Or something like this.
Absolutely.
So that was an assumption, and it was even somewhat tested in practice, like people were doing it, and it looked like maybe it is true. And
it's not, in fact. But here's the point. Here's why people didn't find it. Because if you pick some words, their neighbors are all really kind of do lie in a flat space. And so local PCA on them, as just as you suggested, will suggest, hey, this thing looks like a manifold. The point, however, is there are some words, some tokens, where it doesn't look like that. And so the question really is not so much, hey, are there some points that look like a manifold nearby, but rather the opposite. Do all points look like they have a manifold neighborhood? Yes or no? That sounds like a testable hypothesis. And effectively what the paper describes is it says, great, let's be systematic. Let's go through every single token, look at its neighbors, and ask the question. Would I suppose that that neighborhood around that token looks like a manifold? And scan through, recognizing that some of them are going to have false alarms. This doesn't look like a manifold just because the words are weird and there's some noise and that kind of thing. So fine, statisticians know how to do this. This is a multiple test scenario. So we can do a multiple test correction to say, all right, what's the likelihood that one of these things is going to go bad by random? Let's go ahead and do the multiple test correction, and once we've done that, even one point whose neighborhood doesn't look like a manifold means the whole thing's not a manifold. And okay, so we ran this on 4 somewhat old open source models. Think of this as a paper describing a method rather than testing the latest and greatest GPT whatever. This is saying, hey, I can tell you how to test if your space looks like a manifold. And on those 4 models we looked at, GPT-2, kind of old, but open source, Lemma, Mistral, and Pythia, all open source models. So we have all of the weights, we have the entire structure. None of them are manifolds to a very high degree of statistical certainty. And that's kind of surprising.
Mm-hmm. And it has vast consequences.
It does.
So what would be the examples of?
Right. So the question then is, okay, I've said certain tokens are, the space is not a manifold there, whereas others, it looks like a manifold. The ones that don't look like a manifold tend to be tokens that are parts of words that are homonyms, as in they have multiple meanings. And so, for instance, one of the ones which is my favorite is in GPT-2. It's the token AUNDER, whole word, AUNDER. What does that spell in English? Nothing, right? But tokens can be fragments of words. So what happens if you prefix that with an L, which is also a token? I have the word launder. Oh, well, I can think of a lot of senses of the word launder, like, oh, I need to clean my clothing. That's a good thing. And all the senses associated with doing the laundry and washing things. On the other hand, I can think of a rather negative sense of the word launder, wherein I'm laundering money. Oh, these two senses, if they were to be separate manifolds, have collided upon the word launder. And it happens, though, that the prefix has been left out for some reason. We don't quite know why. But the point of the matter is what this is saying two families of meaning have collided. And in fact, if you look at, we have a table in the paper where we show you all of the places where it's definitely not a manifold. As in all the tokens where these are definitely not a manifold, all of them have the possibility of these multiple interpretations. What this means is, if I'm trying to think about doing a sentiment analysis and I run across one of these words, trying to perturb the meaning of that text is not going to work.
That's a great example. What about hallucinations? Do you think hallucinations can be related to the to this kind of issues of manifold crashing?
Yeah, actually. So one of the interesting things happen is sort of a geometric reason. So if I have two surfaces that fit together like this is a two-dimensional manifold, this is a two-dimensional manifold. I have 2 degrees of freedom I can move on my hand along the fingers and across the fingers. Same over here. So if they fit together like this is no longer a manifold where my fingers join together. This is a singularity. If you were to do PCA here, you would realize that there's no sense of what the proper dimension is. Mm-hmm. Now, if I'm happily going along here, my large language model is working over here, well, okay, due to the fact that the transformer architecture yields smooth maps, or at least piecewise smooth maps, continuous in any case, it's entirely possible I might fall off of the manifold a little bit. Well, if it's just like this, hey, there's a nearest point I can kind of come back. Approximation is totally fine. Totally approximation works. And I'll get back to something sensible. But if it looks like this, and I'm over here, I don't know if you can see that. If I'm over here, and I kind of ever so slightly end up over here, suddenly I could snap onto the other side. So what this means is the sense of meaning over here, the positive washing my clothes sense of the word launder, is what's the topic of discussion. Mm-hmm. But over here, I might have fallen into suddenly the type of corruption sense of the meaning. And in fact, we've seen this with the way that GPT-2 fails to do arithmetic. If you look at the output, if you ask GPT or various other large language models to do arithmetic, they're famously bad at it. They don't really get the meaning of arithmetic. But it turns out in the case of GPT-2, there's a really clear reason GPT-2 fails badly. And the clear reason is found in its behavior. Instead of answering the arithmetic query, like what's 5 plus 5, instead of giving you a number out, it very quickly runs off and starts telling you about current events, or at least what were current events during its training data. What? Well, it turns out two senses of meaning have collided together. The sense of meaning of numbers and the sense of meanings of time. Days of the week do actually have a numeric property. Days of the year have a numeric property, but they're also time. And what's near days and months and years? News stories and current events. So it's actually a short hop from doing arithmetic to talking about current events.
Is it on a level of literally the numbers? So, for example, if you try to do arithmetic of 6 plus 12,
Yes.
you're likely out because there is 12 months.
Yes.
If you are 337, you might be less likely to go out.
Yes.
It is that level.
It is like that. It is
so
like
cool.
that. And it's in a way where other large language models that for whatever reason, whatever circumstances they're training, the numbers are not really near the days of the week or the months, the years. And so they're more likely to stay on topic in a sense, because there's nothing nearby, no smashed in sense of meaning to have you accidentally hop onto.
This is amazing. I wonder, there are many examples of this as weird hallucinations from newer models. One famous one, I think maybe you heard it, is the pizza recipe. So you heard about this one? So there was like people were asking about how to make pizza, and the recipe with pizza included, and at the end put a glue on it, right? So I'm just wondering, it might be something about the nature of glue that is like gluey and it looks like a sauce. Maybe there is that crash of two manifolds.
Sure, it's entirely possible, and it might even be. It might even be because the training data has some description of pictures. They may intersect on those descriptive words that are nearby.
It doesn't need to be exactly.
It doesn't need to be exactly the words. It just needs to be the word neighborhoods. And just sort of to put a really fine point on this, and this is, you could say, all right, great, you have this test. How hard is this test to run? This test is actually very easy to run. And this came out of desperation, honestly. So in my sort of broader research as a mathematician, I tend to study topology, which gets you very deeply down rabbit holes. And there's been a push in recent years toward doing computational topology. As in, I want to compute something about this. Like, I know, for instance, I'm looking at this microphone holder and it's got a bunch of holes in it. Well, how do I count the number of holes in that? If you were to, like, say, take a laser scan of this thing, how can I count the number of holes? Well, there are mathematical tools in topology to do this. There's mathematical tools for testing something as a manifold. But here's really the basic idea, and it's very, very simple. But out of desperation, I said, well, can I use these tools on these large language models? And what happened is they immediately crashed. Like, ran it on my computer immediately runs out of memory. What? How could I ever do this? I said, well, I got to do something simpler. Here's the simple idea. And if I may, let me tell you the essence of the algorithm, because it's very simple.
Yeah.
From middle school, you probably know the area of a circle. It is?
PR squared?
Yes, absolutely. Yeah. Perfect.
Well, that was a test. I have PhD in computer science. I should know that.
Right. But the point is, all right, the area of a circle is pi r squared, right? Great. Right. Fantastic. I'm not going to ask you the volume of a sphere.
Surprising, What?
What? Okay. Right. What's the volume of a sphere? Oh, it's something involving pi times r cubed.
Yeah.
Oh, notice the r squared r cubed, the exponent. It turns out, if you're on a manifold, if you really have a manifold, the volume is proportional to r to the dimension of the manifold. That proportionality constant's where there's things involving pi. And this is an approximation, but it's a good approximation. Oh, well, if you look at the data, how do you know volume? Well, you can count the number of neighbors is a proxy for volume. So on the left side, I count the number of neighbors a word has. And on the right side, I measure the distance between the words using the coordinates that were given to me. And then all I try to do is find the exponent that fits that relationship.
No, but I need to understand the volume in this. Well, the volume, if you would use Euclidean measure between the distance of the words, you get some kind of volume. But you are saying the number of words. The number, right. Would be there. So volume is measured in the density of the embedded space?
That's right. Yeah, that's right. It's a Monte Carlo estimate. So I mean, it's the classic sort of thing. I want to measure the area of a circle. So how am I going to do that? Well, I'm going to draw a circle on the wall, and I'm going to throw darts at it and count the number of darts that went in versus the number of darts that went out.
So it's statistical measure.
It's a statistical measure of
in
volume.
this case area. And
right. in that case area.
Yeah.
But the point is that in fact, if you have a manifold, it's always the case that you can do a Monte Carlo estimate of volume. Count how many points are in that ball of radius R. That's proportional to volume. So if I then say, let me vary the radius and count how that number of points changes, I get I get a sequence for each radius. I get how many points are within that radius. So I have volume versus radius. All you have to do is find the right exponent to fit that. You now know the dimension. If this were a manifold. Other fact about manifolds, the dimension can't change. So now all I have to do to run my test is I say, here's a token, a word. Let me look at its neighbors, estimate what the dimension is there. Here's another word nearby it. Estimate the dimension there. If those dimensions are not the same, you don't have a manifold. Full stop. That's the entire test.
Yeah, brilliant.
Very simple.
Yeah, and you call these places singularities.
Singularities.
This is a term you used in topology, or you borrowed it from general relativity?
In fact, historically, general relativity and differential topology grew up together. And so it is the same term. It is the same term. A place where I have a space that looks like it should be a manifold, but it's not, that is a singularity.
Oh, great. So it's not, you didn't take it from physics, it's physics and math grew together.
Grew together, and this is, yes, a classic example of a topological singularity is a black hole.
So I bet it will be something with Minkowski.
Oh, yeah. In fact, and actually, some of the computational techniques that led to studying manifolds are, in fact, go back to Minkowski and his intellectual priors.
Yeah, by the way, Minkowski, just for people to know, he taught Einstein how to do differential topology.
That's right. Differential
But
topology
Einstein
and
could have not done it without him.
Absolutely. Yes. Brilliant mathematician. And the computational techniques that we use to measure the structure of manifolds are largely due to him.
Yeah. So that's cool. So you basically have a technique which determines whether something is manifold or not. And on all models you run it, it was not a manifold. So my question as an engineer would be like, okay, how can we fix it? So one idea I'm selling $1 million idea to OpenAI right now.
Fantastic.
For free.
Fantastic.
How about you label all the training data when you have homonyms and other problematic words with an additional token which determines its meaning. So, a C and a C will be C number 1, C number 2.
Fantastic.
Now you have two different things. Did I fix the issue?
Well, so it seems like that ought to do it. And actually, this is a great segue into the other paper, in fact, because the whole transformer idea is, if I'm looking at a single word, the whole idea is to say, what comes next? If, I use the word if, what comes next? Can you guess? No, right?
No, yeah.
Right? But if I say, I give you a long phrase, I can't think of one right off the top of my head now, but if I give you enough context, you can make a pretty darn good guess what comes next. And so your idea of tagging each of the words with some kind of which sense of the meaning do I mean here, that hopefully the whole gambit of the transformer is that's encoded in the context. So it's already there. Now, that sounds like it ought to be great. It sounds like it ought to work. Effectively, to use the math term, if the transformer is properly sensitive to context, it should resolve the singularities. It should eliminate them by way of separating these two smashed together meanings.
But because you already explained that it doesn't work if the context is not attaching that sentence to the surface of the first manifold.
Right.
If it's a little bit off, it might jump to the second surface.
Exactly. And this is why this idea fails. What you've explained is why this idea doesn't work. So effectively, yes, if I could sit down and disambiguate each of the senses of the words in the training data so that every single word is completely unambiguous, then yes, we would have a manifold.
Yeah, but good luck doing that.
Right, good luck doing it. Well, never mind good luck doing that. I submit to you that what you've just done is you've just destroyed sarcasm. You've just destroyed any kind of ambiguity in art.
Yeah.
All of that's gone.
Yeah.
So now, the idea is, well, that's going to be a pain. Let's not do it. So let's use context instead, see how far we get. That's the idea of a transformer. And the lesson of this second paper is that does not work. It is that any singularities that are present in the space of tokens will show up in the behavior of the model if you look in the right place.
This is very interesting. So as a theoretical statement about the entire model, you've proven that it will not work.
That's right.
Now, what are the practical consequences of it? What does it mean in practice?
So for instance, what this means is, so we tried this. The second paper has a detailed mathematical proof that in general, any singularities that are present in the space of tokens will show up in the output of the model. And there's a technical thing. It says, provided that the internals of the transformer break enough symmetries, which in practice they do because there's noise. So the question then is there a practical effect? And what we did to sort of say, oh, well, if this idea works mathematically, can we try it? So we took one model. We didn't take all 4 models that we played with before. We took Llama. And the reason for that is simply because Llama runs fastest. And what we did is we said, all right, great. Hey, Llama, let's ask you what happens when I start talking to you and hit one of these places where there's a singularity. Can we cause these abrupt shifts in meaning? And the answer is yes. We can cause this. Hallucination is a funny word. It's not really the right word to use in general because hallucination implies that there's some stored understanding and meaning, which if you are largely quoting or summarized quoting text, I'm not sure there's meaning to be had. And so what I've told my students when they ask about hallucinations, my general answer is that the hallucinations that you see in the output of these models are actually in your mind. They're in your expectations about what the statistical data look like, and they're wrong. So, from hitting the practical sense, if I give a model a query, or I give it some text, and that text has some of these places where it's not a manifold, and I were to change that, you should expect the output will be dramatically different semantically. i.e., prompt engineering is specific to that model. I can't transfer the prompts that I've used to tune whatever, pick your favorite model, into another model. That's one of the major practical consequences. And the moment any one of these models gets retrained, you have to redo your prompts.
And it also implies that prompt engineering is way more powerful than we thought.
Oh, yes. Absolutely. Without a doubt.
Yeah. So let's go to some examples how powerful it is. This will be the scary part, like I think, at least for OpenAI and Meta and so on.
Right.
So what can you do with this prompt engineering? What do you think is possible, at least theoretically, not necessarily?
Right. So it's a funny thing. You could say, how do I pull this internal structure of the model out? Because that's what the second paper says. Says you can pull the internal structure of the model out. Well, how? Well, it's actually very simple. You don't talk to the model as if it were a human. You don't use it as chatbot chatbot structure. You talk to it with single tokens. And the discipline then is you go through the list of tokens and you say, I'm going to give you a query, and that is all that is in your context window. So you reset the model, give it the token. I mentioned AUNDR, for instance. And that is my entire query. See what happens. Record the output. Stop. Save that result. Throw it away. Throw away the query. Save the result. Throw away the query. And do another token. Repeat. You now have a table that says token that I used as query and response. Do this a bunch of times for each token, so you get a distribution of possible outputs. These are statistical models. And if I can get on a soapbox for a moment, one of the things that is important when you're talking to a statistical model is you got to build up statistical significance. N equals 1 is not statistically significant. So run the same query a bunch of times. So you have a table now. The table lists all the tokens, multiple runs, and what the response of the model was. Oh, well, Now all I do, if I want to understand what the topology of that space of tokens was, be it a manifold or not, I just measure the distance between each of those responses using your favorite word metric, of which there are many. That gives you brand new coordinates for each of the tokens. So I now have that internal structure in hand. So now I can say, great, if this model were proprietary, I can still tell you if it's manifold or not. Mm-hmm. But now even better, look at what the output is. Because what tends to happen is that these kind of very simple queries are what are sometimes called glitch tokens. And the idea of glitch goes back to how people do reverse engineering of hardware, computer hardware. They send in small pulses to kind of screw up the system a bit and get it into a weird state, and then it does something coherent out the other end, and you kind of reverse engineer what's inside. It's a tactic for understanding what's the inside of some kind of system. Glitch tokens have shown up in the literature. People have written about them, said, hey, it's kind of funny. You know, if I took my keyboard and I went mash and dumped that into ChatGPT, as many a bored student probably has done, hey, it takes you seriously and responds with something coherent almost every time. And that's what we found. The surprise then is, well, what is it saying? Well, I mean, I'll tell you this. When we tried prompting lemma with one of the tokens happens to be O followed by T, 2 letters. What comes out is coherent LaTeX code for specifying a figure. Oh, that's interesting. And repeatably so. It's memorized data. So this process of using non-semantically coherent, like unmeaningful queries, yields coherent, apparently memorized data. Now, is this really in the training data? We don't know. Mm-hmm. But I don't know where it would have gotten it otherwise.
Yeah, the probability that this is a random output, it's kind of low. It's like this famous story of if enough monkeys can ride a omelet, right?
It's exactly that. Yeah. It's exactly that.
Well, so that would suggest that there are potentially exist queries that could retrieve the fragments or not to say exactly the training data, but close to training data probability. So let's say there is now the famous case of New York Times suing OpenAI. There possibly exists a query that could retrieve 90% plagiarized New York Times article.
That's right.
Not necessarily 100% because we are talking about regression. Yeah, kind of, but 90%.
Yeah, it's possible. It is entirely possible. Now, is it one of these single token queries? Probably not. But the fact that single token queries can pull out semantically coherent, apparently memorized data really strongly suggests that there's a lot of stuff in these models that has been memorized and could well be plagiarized by never mind legal sense. I'm not a lawyer. But from the academic sense, what this means is if a student is using a large language model to create answers to a homework assignment, there is a high probability that that contains material that would meet the threshold for academic plagiarism.
Mm-hmm. Well, there's also, from ethical point of view, there is not much difference between that being copied from somewhere else or generated by a model, maybe from legal, but from practical, you're still cheating.
It's still cheating one way or another.
Absolutely. Did it for you. Right. Yeah. But this is so interesting because my understanding of transformers, by the way, the guy one of the guys who invented transformers was a guy at my university. So we were studying together.
Cool.
I'm so excited about it. Because it's my little university in Poland. But so basically what it means is that the claims, because, understanding transformers on a basic level,
sure,
I agree with the claim that they don't have memory, right? Obviously, like they are changing weights. It's not a normal memory structure.
No.
There's nothing saved, right? Like people think that OpenAI is like saving or that.
No, that's what Google did. That's what Google did, right?
Right, exactly. The new version is you don't save it.
Right.
However, what you really do, you are embedding it or compressing it into the weights.
That's right.
To such a level that you can retrieve it with high probability. And that's
absolutely
equivalent semantically, like at least legally maybe, to memory.
Yeah,
right?
It feels like a kind of memory. It really does. I mean, the argument could be made that what is a transformer? It's basically a way to try to estimate a conditional probability. Given I've seen a sequence of tokens or words or what have you, what comes next? If you try to build that out as a matrix, a probability matrix or an array, I need to find out, okay, given the fact that I've seen all of these tokens, what comes next? Most of these sequences of tokens never occur in nature. So the probability is going to be 0. But just a priori, it's a big array that I need to fill. Need lots of samples to estimate that statistically, right? And so the idea of the transformer is twofold. First of all, figure out where the zeros should be. Effectively, this is like figuring out what the grammar of the language is. These are prohibited sequences of words. And then the other thing you do is you say, well, there's just too many words. Let's use a token or word embedding to reduce it down from 50,000 English words down to 700 or 1,000 dimensions. Much, much smaller space. Those two together, however, mean that, yeah, it's a smaller space. It's not going to recover exactly, but it's really a regression process. It's like asking the question, if I hand you a line of best fit for a bunch of points, can you recover the points? No. But if all of those points were really close to the line of regression, yeah, sure. And so the question then is, if this space were to look like a manifold, then we can definitely recover that. The fact that it's not means that recovering all the training data is going to be hard. But recovering some of the training data, especially those places where something interesting happens, those non-manifold points, game on.
So maybe you can elaborate on that. Why is it easier to recover the places where the manifolds clash and you have singularity?
So it turns out when you look for them, when you look for those points, doing this dimension argument that I've done, these are places where the output, when I send in a query, is unstable. So if I send in the same query, get single token query, for instance, I get some output. And I said, you need to rerun this a bunch of times to get a distribution. Great. If it's near a place which is probably a manifold, not near a singularity, that will be pretty stable. If it's not near a manifold, i.e. it's near a singular point, that's going to be unstable. Right away, you can see that there's variability in the output. Very easy to detect that.
So you basically literally see that the output is similar in the first case when a manifold is stable or it's actual manifold, and not when it's not. Wow, that's so interesting. Yeah. And you have examples of this. Yeah, that's very cool.
Right.
Yeah. So and another question I had about this is you actually try to generalize the question. So if it is not manifold, what it is? Right. What is it?
What is it? Right. Yeah. This is the classic statistical discipline, which philosophically goes back to the logical positivists, which goes back to falsifiability. I want to know, is this hypothesis true or false? Oh, well, but if we're doing science, we can only tell if it's false. I can posit a hypothesis. The tokens are sampled from a manifold. False or don't know.
Yeah.
And so I can say false.
People keep forgetting that.
That's right.
It's one of the biggest problems in society.
It is indeed, right? False or I don't know. Great. So, okay. So in these 4 models, we found very much false. The probability that these are manifolds is like 10 to the minus 8. Very, very small. Great. So then, of course, your question is very, very on point. Well, what could it be? Let's pose a more general hypothesis that includes manifold and see if that's going to reject or not. And so a very natural thing to do is to say, well, all right, what do I do? Well, you say, is this cup a manifold? Well, the inside of the cup, like inside the clay or the porcelain, but it has a sharp boundary. Yeah. A sharp boundary does not look like Euclidean space because it's half of the space. Half the space is missing. Yeah. This is not a manifold. This is a manifold with boundary. So, great. What does volume versus radius look like on a manifold with boundary? Oh, well, here's the interesting thing. If I'm deep inside the porcelain and I have a small ball, it looks like a nice manifold. But as soon as those balls, the radius is large enough, it starts to pop out of the surface of the porcelain. Do I get greater or smaller number of points? Oh, well, there's no porcelain outside, so I get a smaller number of points. The volume necessarily goes through a transition where it's increasing and then it suddenly decreases. It increases at a decreasing rate. It's derivative drops. So you can test to see, is this a manifold with boundary? Or a nice way to think about this is say, is this a manifold that's been thickened up? And that kind of structure is a kind of fiber bundle. It's a fibered manifold. So in the paper, we say, well, all right, let's suppose that, okay, maybe it's not a manifold, but let's suppose it's a fibered manifold, a fiber bundle. Run the same kind of test. The same kind of test now says, let's estimate volume versus radius, and instead of having one dimension, let's find 2 or 3. And ask, is it ever the case that the volume decreases? If so, it could be. It's consistent with a fiber bundle. So again, we're looking for a rejection. We reject this hypothesis if suddenly we find more points. And as it turns out, when we run this on the same 4 models, we find 3 of them. GPT-2, Lemma, and Mistral also reject this fiber bundle hypothesis. What that means is, that there are singularities in those spaces that are even more complicated than just falling off a boundary.
Yeah, it basically is even less structured than we thought, even less smooth than we thought.
Even less smooth than we thought. That's right.
Do you have any statistics on how, in terms of numbers of tokens, how many singularities you have?
Yes.
Because if you have 1, then you've proven your point, but we kind of don't care.
Sort of dumb, right? That's right. So if you look at how many points are singularities, not manifold, order of magnitude 100. So you can go through the list. I have in the paper on arXiv. I haven't put it there because it was just a massive list. But if you ask for how many places does it violate the fiber bundle hypothesis, we're talking tens. So in fact, in the paper, I list them all. And those are them all that reject to the 1 out of 1,000 level, p less than 0.001.
So this is, well, kind of small number of tokens which do that.
Yes.
But that depends on the complexity of the model. So every model will have, is there any relationship that the more complex model, the more you will probably have?
No, not necessarily. So actually, here's an interesting thing that we found. So Mistral and Lemma are a good test case. Both open source models, both trained on roughly the same kind of data, both sort of fine-tuned for math and code. They have exactly the same tokens. So we can side-by-side compare these guys and say, all right, token, 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 they're the same tokens. So I can look at their neighborhoods. I will tell you that the tokens that reject the manifold and the fiber bundle hypothesis for these are totally different. What this means is the underlying internal structure of the spaces for these 2 models are vastly different. What that suggests is that training methodology completely determines the structure in a way that is kind of irreversible and like a fingerprint.
And also not that surprising.
No, not that surprising.
Because it's the randomized process. So
it
I would be surprised if it created this thing.
Well, so the...
Oh, you mean the context would be...
Well, so here's the point. If people are really doing machine learning, they're trying to find, the minimum of the loss function. If you're really finding a universal feature of language, and that's the global minimum of language, then they should agree. The fact that they're not agreeing means that you didn't run the model to convergence, or, and this is not an exclusive or, this is a possible and or. That, okay, you didn't run the model to convergence, or you're not actually converging to the global minimum. You're not actually finding universal features.
So you're in a local minimum?
You're in a local minimum.
Not even a minimum.
And in fact, perhaps your global minima are not where they should be. You're not actually even minimizing the right loss function.
Okay. Yeah, I see.
So these models are totally different, potentially, which is really kind of surprising.
It's kind of cool too, you know. It would be boring if all models converge to the same. I mean, maybe it would be ideal, but then there would be no point to have more than one perfect model.
That's right. That's exactly right. So that's an immediate consequence of this.
So in the future, there will be like discussions like, you know, this particular way of training, we don't know how, but it produces better poetry.
Perhaps, yes. I mean, this is providing a quantitative reason for why a judgment like that would be plausible.
But the sad thing about the number of tokens, small number of tokens, is that means that it can be protected. Because let me tell you what I was thinking.
Yeah.
Once AI takes over the world, and we are living in this dystopian future when everything depends on it, I was hoping that we can do something which was in one of my favorite Polish science fiction writers called Godel. He came up with an idea of something like 1984 surveillance world. Fully surveillance world where people speak a language called Koalang, which has completely twisted meaning of every word. So the machines who listen to it cannot understand. So I was like, that's the way to do it. We'll just, speak with tokens that will divert the AI into other idea. But you'd say, well, but what is the solution for it? Is unfortunately that you just list that tokens as forbidden queries. That's it. And that protects the machine from being broken into.
At least in this way, yes. Now, the other thing though that is left open here, that still works, and perhaps even is a source for some future exploration. Again, this method of testing is very easy. You don't have to use single tokens. The space of multiple token sequences is much larger. We know a slice of it is not a manifold. So the whole thing's not a manifold. But there could be other singularities present in that space, and there could be vastly more of those.
So combination of tokens give you larger space to find singularities.
That's right. And we know that space is already singular because of slices. So the point is that there's a handful in the space of tokens where it's not a manifold, it's singular. But there may be vastly more singular sequences of tokens than there are of individuals. And of course, this is where your science fiction idea kind of comes to the fore. I don't ever just use one ambiguous word when I'm crafting a piece of ambiguous poetry or statement. I weave a long web of this, do I not? I use a sequence of words that sort of build this. So it stands to reason. And in fact, actually, here you can kind of see this when I've mentioned this idea that, hey, these large language models, token spaces are not manifolds to some people. Some people are justly surprised. Some of the AI researchers who've been around for a little bit longer have said, this isn't that surprising because we really expected language to be the way the linguists describe it, to have a hierarchical structure, to be nested. None of those are manifolds. Furthermore, if language is rich enough to describe something like, I don't know, any one of the wonderful paradoxes in mathematics, pick your favorite mathematical paradox, Russell's paradox, for instance.
Gödel is my favorite.
Or Godel or whatnot, right? Okay, I can express that in language. If language is expressive enough to say that, it almost certainly has to be the case that the space of sequences or tokens is not a manifold.
Wow. That's super deep. So let me understand this. So are you claiming, for example, in case of Gödel incompleteness, that Gödel sentences are clashes of manifolds?
They're clashes of meaning, for sure, levels of abstraction. And if, in fact, those words that you're using, sequences of symbols perhaps, and Gödel numbers, if, in fact, they were to lie in a manifold, then those manifolds have to collide and build some kind of singularity.
But would that mean that there is another language where the Gödel, that means even from Gödel theorem it means that. But I just realized that I'm saying,
yes, you've fallen into the trap, haven't you?
Another language would have another Gödel sentences in it.
That's right.
That's the whole point of the Gödel.
That is literally the point of the theorem, is that this is inescapable.
So it's inescapable regardless of the language.
That's right. So
that means, can I draw this line this way, or it's too much? That means that there is no language set that will have no manifold clashing.
That's right.
There's no such language. They're above arithmetic.
Okay. So the point is, if the language is good enough to express math,
Yeah, exactly.
And as far as I know, all natural languages are expressive enough to do that. Then they cannot have manifolds for
Not
linguists.
even the hallmarks, just arithmetic, right?
That's right. Yeah. All you need is arithmetic. Yeah.
That's so cool.
It's super deep, isn't it?
Yeah. This is such an interesting, unexpected connection. Does it also mean that you could basically come up with Gödel sentences for the natural language? By the way, are the paradoxes considered Gödel sentences? Like, if a liar is lying, saying that he's
So you have to be
lying.
super careful with these. I mean, the whole point of why the Gödel theorem is so subtle is because what you're doing is you are managing this clash of meaning because you have two separate abstractions. You have the language of arithmetic expressing sort of the base ideas, but then you also have the using arithmetic as a representation of something logical. So you have to be really careful saying, "Hey, I am a liar." That statement involves a self-reference that is hard to take apart. The whole point of Gödel's incompleteness theorem and sort of the history of how it came about, the history is that it came about from trying to resolve Russell's paradox, which is exactly that sort of does the set of all sets contain itself?
Yeah, exactly.
Right? And that's effectively equivalent to the liar's paradox.
Yeah.
And the resolution that most mathematicians subscribe to is that you have to say that different sets have different types, different classes. So I can say that a set is a kind of class, but there are classes which are not sets. The set of all sets is a class which is not a set.
Interesting.
And it feels a little artificial to do that. And effectively what the Gödel incompleteness theorem is saying is it's saying that if you try to do this class theory thing, that works, but it comes at a heavy cost. Because now you can no longer express things like express the consistency of a theory in itself.
You basically either get incomplete theory, or you get sentences which cannot be proven. That's right. You cannot get both.
Yes.
Yeah. So there is some relationship to the traditional paradoxes, but it's not like straightforward.
It's not really straightforward. Yeah.
Yeah. Because we don't really have the axioms for the language when we are speaking.
No.
Maybe no.
No, they're statistical in some sense. But I suppose the point is grammar does matter. And the grammatical rules can be used to express certain concepts. But there's this old distinction between the syntax of your grammar and the semantics, the meaning. The two levels of abstraction fit right there.
Yeah.
And that shows up in the Gödel theorem for sure.
Yeah, this is such a super interesting connection. So do you think that there is a way? Do you think there is a reason and a way why for which the training of large language models or even the architecture should be modified based on the findings that they are not manifolds, but they have singularities?
That they have singularities. Yeah. That's a good question. I think I can say I probably don't have a strong opinion on this at this point. Knowing that the whole purpose of a transformer is to make concessions to convergence to estimate this conditional probability. Given a sequence of tokens, what should come next? That does not imply that you have to have the attention mechanism, which effectively is find me the prohibited sequences of tokens and don't bother trying to estimate there. Zero out this array. That seems pretty sensible. I'd say if I had my druthers and were building one of these things, I'd say, well, you start with a grammar because a grammar tells you that. If you laid out what is allowable grammatically, that sort of tells you that. The idea of the attention mechanism is I want to learn the grammar.
Yeah.
That seems kind of sensible. The embedding idea, again, works well when we're dealing with a lack of clash of meanings. And so it works great for sentiment analysis. That's fine. But architecturally, it's sort of in the data is sort of the point. It's in the data. It says that maybe we shouldn't be ascribing numerical coordinates to all words. That's what it's saying. It's saying maybe we need to take a step back and look at some of the older AI concepts back in the early 90s, 80s, even 70s, where people were looking at what does the semantics of a word mean?
Yeah.
Actually carry around that dictionary and use it. Trust the linguists.
Yeah, but the problem with this approach is it comes, I think, from Wittgenstein, right? Back to Wittgenstein.
Sure.
It's really hard to do it for the whole language. It's like you do it on small sets, it works great, and
Absolutely.
then you have oh my God, I forgot the name of the prologue. Yes, you have prologue and languages like this, right?
Right. And maintaining prologue databases is a task I do not wish on anyone.
And maintaining prologue databases for all languages, images encoded, and it's good luck, right?
This is not
so
pleasant,
that was a great technique to avoid that, to learn the grammar rather than specify it in rules, right?
Sure, but even at that method has limitations as well.
Yeah, interesting. But maybe there is some kind of combination of these methods. Maybe you can like embed what we know. It's incomplete, but start from there.
Sure.
Right? Instead of going completely.
Yeah. No,
learn everything.
Entirely possible. I don't have a real strong understanding of is this even something which we should be trying to resolve?
Yeah.
Or merely is this okay. These large language models are neat, but they don't generate language the way we want them to. And so for that, what I've been thinking along the lines of, great. On the other hand, suppose we have actually been given a transformer. Okay, it has limitations in the ways that we've just discussed. Instead of using it as a generative tool, let's use it as an analytic tool. Let's use it as what it is, a model of language. Oh, it's a probabilistic model of language. Let's use it to help us read. So if I hand you a piece of text, and you as a human read it, you parse it, you do the grammar process, whatever it is, you extract the meaning. If there's a lot of text, it takes some time. Wouldn't it be nice to know what parts of text are most surprising? In fact, from a probabilistic standpoint, compression standpoint, the entropy of that text varies as you move through the text. It's interesting in certain spots and not in others. I'm reading through a novel, I got some boring bits, let me skim over those, and then, this is the good part, right?
I use it for papers all the time.
Right.
I tend not to, if I want to read 10 papers, and it is for a podcast, let's say,
sure,
I would rather ask the ChatGPT to give me the gist of the paper rather than read the paper because it's faster, right?
Sure.
Of course, I will miss something, and I might be suffering from hallucinations induced by the
So in fact, what I'm saying though is you're interacting with a chatbot to do this. You're still having it in its generative mode.
Yeah.
What I'm saying is we could actually much more efficiently just grab the transformer and run that over the text and look at the probability of the next token the whole way through. Very simple. Now the places where that probability drops abruptly, those are the places in the text where you, the human, should probably pay attention. Those are the most information-laden parts of the text.
Yeah. It's very interesting, but there's also a little change. I'm kind of hesitant speaking about it because I haven't read the paper I want to refer to.
Yeah.
I just saw it on LinkedIn, so and I reacted to it, but I haven't read it yet. There is a new paper by Anthropic. Have you heard about this?
I have not.
It's written a few days ago. So the paper is titled like a biology of a transformed of a large language model, something like this. So they're pointing out all the similarities between the function of a human brain and the inference in a language model. But they find interesting issues which are the differences. So for one example is the arithmetic. So if you ask a model to add 36 plus 47, it will add it correctly, but if you trace it, they do, the interpretability. If you trace what it did, it was so weird. It's so strange. It will estimate, and it's not that strange actually based on your what you said. It will estimate that 36 is kind of like 30, and 47 is kind of like closer to 50, and then it will add 30 to 50, and then it will say like, but there is this reminder, we need to resolve this.
Sure.
And maybe I have an answer for 6 plus 7, but I already had 50. So now I could combine it. It doesn't do normal, not even a weird algorithm for arithmetic. But when you ask it, how did you do it? It will say, well, and it will obviously give you that like a standard arithmetic of adding
memorized.
Right. So what it proves to me is that it doesn't have metacognition.
No.
Right? Like
no, clearly not, right?
Yeah, clearly not, because it does not tell you what how it arrived to
That's right.
to an answer. they kind of claim that they kind of, try to hide, like in the paper, it feels like it didn't really read it carefully, but feels like they're claiming it is so similar to human. And then like in the page 3, they say, well, actually, like in this case, as we see, it's not in the metacognition. So it's not really
interesting.
Right, I understand
Yeah,
it works against their big, business model of like we are creating artificial general intelligence and so on.
Right.
But it's super interesting, and I wonder if there is a connection. Another example which is even weirder. I also think that that's the case, that the transformers are to predict the next. So it's like a smart regression.
Yeah.
But they show that if you ask a model to create a poetry, it will not go sequentially about it. It will take the last word which matches the previous sentence. So find the rhythm, rhyme first, and then we'll go backwards. So it's not literally like it's not that simple that it goes from the first token to the next token and so on. So a little bit more.
Okay, so let's drive into that. So yeah, from a how is it implemented standpoint, it's predict the next token. However, if I have a long sequence of tokens, and remember what's going on inside this is a probability matrix of which portions of it have been zeroed out. That's what the attention mechanism is saying. As you're sliding along through text, I can have interactions between those earlier terms that only in the end show up in the output sometime later. So there can be a time delay. So in fact, the point is, and this is something very common for all autoregressive processes, that's the statistical class of systems in which I have a sliding window through time, and I have some short block of memory that I'm interacting with. Most of what shows up in the statistical literature are linear autoregressive processes. You have a sequence of samples, and you slide a window of that along, and you do something linear to predict the next. A transformer is a nonlinear one of these. What we'll find that you get periodic behavior in linear autoregressive models. They're described very neatly by Fourier transforms, which do Fourier analysis. Oh, well, if they're doing periodic stuff, that means that patterns that happen early on in the sequence may take a while to percolate out to come out the other end. So it's perfectly reasonable that if I have a nonlinear autoregressive process, such as a large language model, that although Fourier transforms won't work because they're not linear, it still could have that kind of take some time to percolate out.
Is there any equivalent nonlinear modeling of like Fourier transfer but for nonlinear? Does it exist?
They exist in very special cases, so not in general.
Not in general, and they will never exist, or we didn't discover?
We don't know for any of
nice area for math research.
It is. I mean, I have kind of what drew me into this line of research was playing around with sort of constrained nonlinear signal processing, and so I've often wondered about autoregressive processes like this and nonlinear ones because they could do awesome, neat things. In fact, from the standpoint of building musical instruments, digital musical instruments, nonlinear autoregressive processes give you really neat effects that can be controlled. If I were to say, let me make a random nonlinear instrument, it would sound terrible. But if I use an autoregressive instrument with some controlled nonlinearities, it can sound decent and I can have control over it, which suggests that there's something Fourier-like going on.
Yeah, right, because the Fourier is at the end of
frequencies and time, right?
Yeah.
Yes, of course.
That's very interesting, but there is no general.
There's no general one that we know of.
That's so cool. I'm wondering if this we can unless you want to say something more about the papers, it's something which we missed. We can go a little bit philosophical. We're in the second hour, so we can go to the
let's do some crazy philosophy.
Yeah, let's do the crazy stuff.
I mean, I am not a philosopher. I am a mathematician.
Me neither. Well, mathematicians are philosophers.
Oh, are they?
Like Wittgenstein and so on. Let's say. But what I mean is, in this podcast, we often this is the third time I think we are discussing these big claims of these big companies and many MIT educated, especially people, who claim that we are entering an era of
artificial general intelligence.
Artificial general intelligence or artificial super intelligence.
Sure.
But the problem I have always with this claim is that you use the word intelligence. The word intelligence requires consciousness sentience. It requires it
Sure.
in the definition of the word. So you can say artificial general machine learning capability. Sure. But artificial general intelligence has this consciousness component.
Sure.
So what the answer is of this typical PhD from MIT, I'm making fun of it because it's is that where it was created. The idea, I think, is that of course, because the theories of consciousness we have, some of them claim that the complexity of information is the cause of consciousness. So given complex enough large language model, okay, let's not be so limiting. The next architecture involving large language models but having something more will be conscious. Right? What do you think about that?
I think I'd have to reserve some judgment on that because I'd say large language models, they're nonlinear autoregressive processes, and those do not feel like intelligence. Why? What's another nonlinear autoregressive process that I know of? Turing machines. Are Turing machines intelligent? Last I checked, no, they're not. And so that's not a proof. That's not a proof. But if I sort of take a transformer and degenerate it a bit, imagine that as a really big context window, such that would terrify all the data centers being built. It still couldn't fit the phone that's on the table as a Turing machine. You can model a part of it, but not the whole thing. But theoretically, if I have a really big context window, one that fits the entire memory of your phone, it's simulating that. So it really entrains the idea of standard computability theory. And really, what's then the big difference between a large language model, and I'm being limiting in a sense because I kind of know how that works. What's the difference between that and a Turing machine? Oh, a Turing machine works on binary numbers. Large language model works on real numbers? Well, maybe not real numbers. Floating
Fake real numbers.
Fake real numbers. And in fact, if you look at the way that the latest standards on floating point numbers are going, most activity in floating point numbers since IEEE 754 a number of years ago, what you will learn is that, we're kind of reducing back to the binary land, in a sense, which suggests then that this kind of approach is probably coming to its limit.
Well, and also, like, physically, it is a Turing machine. Whatever you run, at the end of the day, is zeros and ones on a GPU. But you said something like, as if it was given. You say, like, well, obviously, the Turing machines are not thinking. The whole claim from these people
is that they are.
Not maybe now, but they can be programmed to.
Right. That is a fantastic claim for which I have no counter.
Wow, but there is honestly, I think approximately 99% of computer scientists believe that.
Sure.
In knowing the complexity theory they believe that, and I don't get it. Like I read, the Penrose book in 1994. I was 14, and I read it, and I was like, I agree. And it's not that you've proven to me that there's some quantum element of mind. What you've proven to me by going through the incompleteness, kind of Godel incompleteness, but he did it on the Turing undecidability. You've proven to me that I see that the left side is right, true, the right side is not, but computer will never do that.
Sure.
You've proven to me that there is something about the function of brain which is non-computational. That's enough for me.
Sure.
But I'm not saying I know how the mind works.
Right.
I'm just saying, for me, it is a proof and a strong evidence that we're non-computational. And then we can go to the what exactly happens. There is this microtubulus. I don't know if you are familiar with this.
I'm not.
It's really cool. Like this, there was this concept that there is basically a quantum effects in the structure of a brain, and physicists initially rejected it. Was like, quantum effects on a mushy, warm brain, not possible. But then there was recently some papers showing that the structure of microtubulus in brain are actually exhibiting quantum effects, even though they're macro structures to a degree. I mean, there's a few hundred atoms, not big macro, but still macro.
Interesting.
Right. So there's evidence of that.
Interesting.
Separately. That doesn't prove anything. That still doesn't prove that.
Hardly.
It's just a little evidence that where we thought the quantum effects could not have happened, they're actually happening. Is it related to consciousness? No one knows, right? There's no proof. But there is another little thingy, which is called the guy who came up with the idea of microtubules is an anesthesiologist, and he noticed what happens with your consciousness when you give anesthetics? Well, it disappears.
Yep.
Why? Well, because we are using gases that the gases are known to do anesthesiology, are known not to affect neurons directly.
Interesting.
So that's like, okay, wait. So that doesn't make any sense. We're using something that doesn't affect the activity
Of
of
the
neurons themselves,
But they remove consciousness.
but they remove consciousness.
That's weird.
What do they affect? Oh, they affect microtubules.
Oh.
Interesting. That microtubules which happen to have quantum effects,
Interesting.
right? So it's getting more and more interesting.
That is quite intriguing.
Yeah.
That-
I this is completely totally fringe for now,
Yeah.
because there's one paper on microtubules, and so
That's interesting.
it's not like we know and now everything is solved. But it at least there's like direction toward physical explanation of
Right.
not traditional Turing machine computation in
So,
brain.
so let me try to come back to earth a little bit. One of the things that all AI systems struggle with, and I've not seen any good resolution of, is the concept of negation. Certainly, if you're writing Prolog, you will run into the problem that you want to specify something or its negation. But this is something that mathematicians have run into problems with as well. This is the source of the dispute that led to Gödel even doing his incompleteness theorem in the first place, is the law of the excluded middle, which is to say A and not A. Is that true or false? Well, A and not A should be false. No one argues that, because a statement and its negation, only one of them should be true. But what about A or not A? If you go with the traditional Aristotelian logic, that's true.
Yeah.
Either a statement is true or its negation is true. But of course, that's not how we use the negation in everyday speech.
Yeah.
It's different. And there was a big debate early in the 1900s about whether we should found mathematics on this or not. This is the basis of proof by contradiction. But is proof by contradiction a reasonable thing in the real world? And that kind of brings us back to those logical positivists saying, if I have a theory, it's scientific if I can reject it, not if I can prove it. So the law of the excluded middle, A or not A, is not necessarily true in science for that reason. And when you start to talk about how do I express negation in language, this starts to become really quite subtle, and is actually the important thing in my mind, that when you try to talk to a large language model about something, they struggle over negation in much the same way that our beleaguered Prolog programmer struggles over negation, and the way that every AI system along the way has. And I think there's something important there. Just in the classical, never mind quantum sense, just if we can't express negation, we're a long way from general intelligence, because humans use negation all the time, and we struggle with this. This is the foundation of the scientific method, is to realize the law of the excluded middle is not valid in science.
Do you think it is embedded in language that we cannot express negation?
No.
And yet can understand it as humans?
No, and in fact, this is a personal habit of speech that annoys people that I have, is that I don't hate double negatives. See how I used it there? And it was intentional.
Yeah.
I'm not expressing that I love double negatives. I don't hate them. You see the difference?
Yeah.
That allows me the ability to apply some subtle control to the meaning.
But why are the language models or AI in general struggling with negation?
Okay.
What is happening?
All right, let's go back to the geometry here. Let's talk about this embedding stuff, if you will. If I want to tell you a word, so a word like, I don't know, coffee cup, maybe that's a sequence of tokens. It gets embedded somewhere in the space. What if I want to tell you a word? What if I want to express the concept of not a coffee cup? Where is that in the space? It's not simply, hey, carve out a hole in that space and throw everything there. That's not the right.
But why not? So my answer,
Yeah.
basic answer would be like,
Yeah.
it's entire latent space without the coffee in it.
Right. You punctured this, right?
Yeah.
But does that really? No. Now I could speak around the coffee cup.
So basically, you're saying that I said something which is maybe technically true, but is useless.
That's right.
Yeah.
That's right. So yes, you could certainly carve that out. And actually, this is kind of salient to your comment earlier. I just thought of this now, where you censor those problematic tokens. Well, you pop them out of the space, ripped out holes in the latent spaces. So you're not allowed to use those words. Effectively, this is like an AI safeguard. It's still possible to talk around those words. And if in fact you really had a singularity there, it's still possible that you'll get the same instability present. That is the thing you must do to sort of, that's the thing you must understand if you're talking about negation. Is it really, no, not the coffee, or is not the coffee cup a different part of the same space? Is it puncture the space, remove that chunk, or is it, no, it's over there? Mm-hmm. So you could say, oh, well, for instance, let me give a very concrete example. War is here. Peace. Is peace its own concept, or is it the negation of war?
This is brilliant. I now completely understand what you mean. Coffee is a hard example because we don't have non-coffee concept. But war and peace.
Well, I don't have the non-coffee concept at all. Yeah. I'm a mathematician.
Yeah.
But yes, war and peace. They're both nouns. They embed to different places. Yeah. But they're negations of each other.
And they are perfect, maybe even perfect negation.
Perhaps.
Yeah.
Perhaps.
In which case it was really like non-coffee existed.
Yes.
Yeah.
Exactly.
So there are some concepts which have perfect negation.
And some which do not.
Light or darkness,
sure.
maybe.
Perhaps.
Another. Oh.
Perhaps.
Well, it's physical.
Yeah, physically, sure.
Yeah.
But the point is, if we're talking about systems that are fully artificially general intelligent, they need to be able to handle all of the generalities of language that we as humans have, at a minimum.
Yeah.
If they're going to be super intelligent, then this is a necessary condition that they understand our language with all of its richness.
Mm-hmm. And that is literally impossible to embed.
It's literally impossible to embed. That's right.
That's basically for me like proof. Okay, not formal proof.
Not formal proof, but it's very strong evidence saying that this is not the way to approach that.
So how is then? I never thought about it. How is the negation actually encoded at all? If I'm training on negated sentences, what's happening?
Yeah, well, all right. It's actually language dependent. My favorite example is this, is in English. How do I negate? Well, we've got a bunch of negating particles. Not a coffee cup, the opposite of peace. We put some kind of prefix phrase. Mm-hmm. And other languages do this too. Chinese does this, for instance. There are several different negating particles of different kinds based on types and based on scope. So I can negate a verb. The particle I use to negate a noun is different. If I'm trying to negate the entire concept versus a specific case, I have a different particle for that. Mm-hmm. But yet, if I'm speaking Japanese, I conjugate the verb into a negative tense. Mm-hmm. It's totally a different thing.
That's then language dependent. Yeah.
It's very language dependent. And yet they all have the ability to express these various concepts.
Yeah, but I'm thinking even engineering-wise on the how it is encoded. That means that there will be tokenization of not coffee.
Yep.
As a separate vector.
Perhaps.
Because
right.
how else?
Right. How else? How else would you do this?
How do you do not? Not is such a strong thing. It like moves
That's
through far away place from coffee, right?
That's right.
And that's like it's a very strange word there, right? If you just embed not and just embed coffee, yeah,
right. Where does it go, right? Mm-hmm. And yet you look at again, this multilingual view has become very valuable in my mind in understanding how to handle language modeling generally, mm-hmm. is to recognize that different languages have approached this problem differently. They've all succeeded. I mean, human language is translatable, perhaps with some loss of sense, but if you sit down with a speaker of another language, you can communicate the ideas. I mean, that's to me an empirical fact. But if we're going to make systems that understand language, they need to be able to pick up that level of richness and detail, which means you have to be able to express negation. You have to express uncertainty. I mean, all right, great. Negation is really difficult in this regard. I mean, the War and Peace example says that very clear. But you could also say, all right, what about how do I express uncertainty? In English, how do I express that something is hearsay? Well, I have to give you a bunch of other phrases, and we have set phrases for doing this usually. You know, oh, I heard that, or we have the infamous weasel words when you're writing to express uncertainty. But what about Quechua, the South American language? It's baked right into how you conjugate the verb. It's right there. Totally different way of expressing that same idea. And it's very, very language dependent.
That's super, super interesting. Then, yeah, the not example is brilliant. I need to talk to some people who train LLMs, and ambiguities is also, we already talked about ambiguity comes from homonyms. I had one more question which I forgot earlier.
Sure.
So homonyms is a good example. It's easy to understand. But what about the words which are so common and they come in so many contexts, like in?
Or prepositions.
Prepositions.
Prepositions, yes.
So, yeah.
And furthermore, prepositions are sort of infamously untranslatable. In fact, actually, timely you bring this up. So I am very much addicted to Duolingo, and one of the blogs they had expressed the fact that prepositions don't translate well. What I use the word in for in English, if I were to say, well, in is closest to, say, in Spanish, maybe en.
I totally get it, because my first language is Polish, and I still don't understand why you say at school.
Right, exactly.
At?
Right.
In
Why?
school.
It's,
In school.
Right, yeah, exactly the point,
in
right?
school.
Right. But I mean, there's enough of a matchup that you got to say these guys correspond, and then what? Where did that come from, right?
And there are weirder ones.
And there are weirder ones, right? And again, okay, great. These are languages that have prepositions, but what about classical Latin? Classical Latin, they don't use prepositions. They decline the nouns. They sound change the noun. Oh, and those have very different usages from the prepositions, and that then means that word order is very free. So this whole notion now of laying out your grammar in terms of word order, which is what the transformer with attention, the attention part is about, suddenly doesn't work as well for classical Latin. Oh, well, that's interesting. That means now that these words are really very ambiguous. Lots of senses of meaning clash together. Now, I don't remember offhand, looking at the 4 models that we looked at, where prepositions ended up. If I had to guess, I think they probably ended up far from the others, which is to say, this space of tokens is not a manifold, generally not a fiber bundle, and it's not connected. There are pieces that are floating away off on their own, and I think the prepositions are like that. But I don't remember exactly. But what this means then is if I have points that are far away, disconnected from the rest of the space, effectively the transformer model is reducing to a Turing machine.
Yep.
It's no longer continuous, or it doesn't matter. So this is telling you that when we start talking about language and how we express that, all of those particulars of the language are now embedded into the model in some way, and they don't translate.
This goes to kind of big philosophical discussion whether language comes first or not, right? What I mean by that is if you believe, maybe that is too strong statement, but maybe. So if for people who believe that brain is a Turing machine at the end of the day, not even quantum computer, but like regular computer. The argument that the language comes first is good argument, because it's like you embed the programming functions, like the actual operations into neurons, and then you operate on it.
And the neurons look like circuits.
Yeah.
We know what to do with circuits.
And we program them with language, right?
Yeah, absolutely.
And then you can train yourself like a neural network, right? And there is definitely element of it, because we can learn from language, we communicate with language, improve, but there are some counterexamples. One is like, if you were born deaf and mute, that would mean you can't have a language.
That's right.
How would you have language, right? But people do.
Sure. They have other forms of language.
How did they achieve a language if they don't have that language, that ability to be trained externally, if this is a neural network that's trained, right? So what I mean, I don't believe in the idea that language comes first, like the kind of Lacanian, idea maybe.
Sure.
I don't know what it is, like how the brain works, but I think we're limiting our brain with language, depending on the language we know.
Yeah, absolutely.
But we're not exploring this. It doesn't tell us everything about the structure of thought when we only think about language.
Sure. I mean, there's the classic Einstein quote. I rarely think in words at all. Pictures.
Well, that's a great point. Yeah.
Okay, and certainly as a mathematician, sometimes that is accurately capturing sort of my experience of mathematics. That, in fact, for me, it tends to be tactile even, that I can feel how I'm manipulating mathematical objects. Of course, I'm not moving my hands around necessarily, but I can. It's not words, and yet mathematics is a fundamentally language-grounded thing, and yet so I'm working through the nature of language, using very non-linguistic, tactile even, thought processes.
So maybe this is like the ultimate argument that's a very good point, that we think visually, but that's not the same as embedding these visuals in language of zeros and ones.
That's right.
That's not the same thing.
No, I don't think it is. It seems rather, it seems that there's certainly an aspect which is true. I mean, I keep coming back to sentiment analysis. It does work in certain cases, but does it work in all cases? It doesn't seem to. And it seems like this is one of those the exception proves the rule kind of thing.
Exactly, yeah.
To say that maybe not.
So what do you think is the difference between human brain and a computer?
Well, so for one thing that I think is important, and this comes from the hardware. Yes, computers have this very fine structure, but there's a definite ground state. Where's that definite ground state? That definite ground state is, yes, quantum. I mean, a transistor is a quantum thing. But it's a big macroscopic quantum thing. I mean, I remember back to my electrical engineering days in device physics. Yes, they're quantum, but they're quantum and statistical, and they're using bulk phenomena, turning on and off things. Okay, great. But what about a neuron? And what about all of biology? All of that is, all of it, all the time is happening at a definite lower scale. It's chemical. It's physical. It's structural, and it's also conceptual. All of these levels of abstraction are working together. Now, in a computer, we do have levels of abstraction. The phone sitting on the table, at its bit level is running code that has device drivers and operating systems and such as well. But that base level is logic, Boolean logic. Whereas the base level for a living thing, be it a conscious entity as we understand them or just purely a living thing, is a very messy parallel process. Which, yes, a computer is a parallel process, but it's fundamentally very ordered.
It's interesting that as a mathematician, you didn't use the way you explain, I agree with you 100%, but I always thought, and I'm not a mathematician, very simply, I might be wrong about it, that computers are Aleph 0, we are continuum. That's it, right? Like I thought it this way.
That's funny.
Right?
Yeah.
And there's a big difference between these two infinities.
No doubt. Yeah.
Because what else it is? Like we say the computer is broken. We literally have problems right now when the transistors start to exhibit quantum issues.
Oh, yes.
That's why we cannot put more of them, because they start to jump, into superpositions,
in weird ways. Yes.
Yeah. So that's why we're like, that doesn't work. It's no longer a computer when the electron is superposition on two paths. We have to make it into discrete machine, right? We force it into discrete machine. We don't do that with our brain. Our brain is without a doubt not a discrete machine. Even if you don't want to, even if you want to question these ideas of quantum operations, but it's biologically, physically not.
It's not that, right? Even more so, you're hitting on something else with the brokenness. So one of my hobbies is restoring old computers, and by old they're like the 70s. It's interesting because the hardware is aged to a point now where you get on a somewhat regular basis, and by regular I mean like once a year or so, you get equipment failure at a single gate level, or a single transistor level, or a single wire level, effectively. This brings the computer to a grinding halt. 1 bit off brings the machine to a standstill. I'm pretty sure 1 bit off somewhere in me does not bring me to a standstill in quite the same way. And you could say, okay, fine, I could build a resilient computer that's somewhat more resilient. How do I do that? Oh, I make multiple copies. And there are some famous examples of machines that are highly parallel. But even then, a small number of faults brings the whole thing down. And so it seems to me that consciousness or not, really the question is about robustness. Our ability to think and to be a continuum kind of device, if you will, really comes down to the fact that we can weasel our way mentally and physically through the world, make sense of the world, in a way that for a computing machine, if one piece is off, it doesn't work. Mm-hmm. And so that robustness is kind of important, I think.
Yeah, and for me, it's even another aspect is very interesting. Well, how come we have a temporal consistency? Right, so the first,
do we have a temporal consistency?
Unless we drink too much. So the
well, what about dementia? Then you start to lose that temporal consistency.
Yeah, sure. I mean, sure. There's a lot of issues. What we don't even really know if time is continuous and so on.
Sure.
But what I mean, like we have an impression that we have a temporal consistency. Since I was uttering that sentence, and it still makes sense from the beginning, and it's not complete. Bullshit, right? So that requires to not only that, like single sentence, okay, but I have consistency back to when I was born, more or less.
Sure.
There might be some variations. Certainly. I still am me, and I think I'm me, and was not somebody else. I don't think I was somebody else. Indeed. Completely. Even if I evolved, it's a continuous function without. Sure. Seems to be continuous function, right?
It certainly has the impression of it.
Right. So that's how is that possible on a system which relies on and not too many errors. It just doesn't feel like.
Not only that, it's a very standard thing to break that temporal consistency on a computer.
Yeah.
Oh, what is that? Oh, that's operating system updates.
Yeah.
That's a thing we do. You replace portions of the software, and it is literally no longer the same machine. I mean, it's again, to kind of go into the hacker weeds a bit. This like taking your old Windows computer and putting Linux on it. It's no longer the same machine anymore, right? Yeah. It really is different. It feels different. You interact with it differently. It has no memory of being a Windows machine.
Mm-hmm. Yeah. So that means the hardware has nothing embedded in it. I mean, you can have a hard embedded systems which are printed into.
Oh sure. You can have a ROM, but that is something which is also alterable.
Well, that's something which we differ because. Well, to a degree, because part of our brain is like
is hardwired as such. Yes, absolutely.
And some parts of it are not. Breathing is kind of hardwired.
That's right. Breathing is hardwired. Although many of these kinds of processes that you think. So if at one point I was in a car accident and had to rebuild and relearn how to walk, and that took time. That process of rebuilding. Altered fundamentally how I physically interact with the world.
Yeah, it might have been that you needed to use a brain of plasticity to use other part of the brain.
Without a doubt. So actually, one of the interesting things that came out of this is that due to the surgery itself, some of the nerves were displaced, and so there were portions of my leg where if you touch in one spot, I feel it mentally somewhere else. But now that's been 20 years, and that no longer happens.
So the brain did adapt. Yeah. So it's both flexible and embedded. Interesting. Yeah. Well, because nobody planned it this way, right? No, it was not like it was like this part will be the ROM. This is like a RAM.
Right. It grew that way. We don't grow our computers.
There are some biological companies
but generally speaking, the machines we're talking about, we don't grow them. I mean, in some sense, if you look at software does have some notion of growth through time. Like if you look at the Git commit history of your favorite project, you can see something that feels a bit like evolution. But is it really, or is it not? Is that really us imputing that on because we're the ones alive doing this.
Yeah, I don't know if it would be truly evolution because there is no Darwinian.
Well, there is a selection. There is a selection pressure. I mean, dude, if my program is broken, there is selection pressure.
That's a good.
I mean, there really is some selection, but
Nobody will use it, right?
No,
So
right.
selection pressure.
That's exactly right. Yes.
Yeah, that's cool. Yeah, but machine learning feels more like more evolutionary than standard programming.
Yeah. I mean, what is stochastic gradient descent but a form of limited Darwinian evolution?
Exactly right. Yeah.
I mean, it's limited in the sense that it doesn't have access to necessarily, at least not a priori, the local and global structural control that happens at a genetic level. So when I look at mutations in a genetic setting, those mutations can be single point mutations, fairly limited scope, but perhaps a big effect. They could also be crossovers and have larger effects. They could be metagenetic, so I could have, or epigenetic, that happen in mitochondria as well. Point is, these perturbations happen on multiple scales. Mm-hmm. Whereas when I'm looking at the way that I implement stochastic gradient descent, it tends to be just fuzz up and move.
Well, it tends to be you don't learn the structure.
That's right.
You embed structure is given. You learn the weights of the structure. So it will be like modifying
the hyperparameters as you go along. That's not a thing people do.
Yeah, exactly, right. But I mean, not even. Yeah, well, yeah. You can think about it. I don't actually know. Maybe people are doing dynamic hyperparameter.
I'm sure people try. I'm sure people try, and they probably. I mean, if I had to guess, it's very unstable.
Yeah, because it's too big space, right? So you're basically, it's like changing the whole genome. It's like, that genome, let's make this genome, right? Almost.
And so most of the space is not useful.
Yeah.
So it's like saying, okay, I'm gonna build you a new program, and the way I'm gonna do it is I'm gonna hand you a random bit sequence. Do you like that? No, you didn't like that. All right, let me hand you a different random bit sequence. Yeah. Do you like that? No.
Maybe not that bad that it's random, but I mean, like, know, how about I give you 200,000 neurons? Oh, you don't like it? 300,000.
Sure.
Oh, and they are all connected, or actually partially connected, right? It's right.
There's a lot of degrees of freedom there.
Mm-hmm. Yeah, so it's basically an unexplorable space. So you have to settle with a given architecture. Right. Yeah, that's probably obvious for anybody who's like building it on a daily basis. So
not me.
Yeah, no, not me either. I'm using them, but I'm not building from scratch because I happen not to have $100 million to train a LLM. You know,
maybe if someone wanted to fix that, that would be great.
Yeah. So another maybe a little controversial question. So do you think like your method or something similar might have been used in a DeepSeek? Mm-hmm. So, DeepSeek is suspected and it kind of admitted a few times that it's not an original model, right?
Yes, indeed.
So could you imagine using this kind of technique or maybe some variation to retrieve the training data or not the training data itself, the structures. So you don't need to train from scratch. So you can make it for 6 million like they claim.
Sure. So I think the point here is you certainly, I mean, this is detailed in a mathematical proof. You certainly can recover the token embedding. That is without a doubt, provided the context window is large enough versus the number of tokens you're collecting on the output. That's a hard constraint in the theorem. Provided that's satisfied, you get the token embedding. It might take a long time to do this because you submit a single token a bunch of times to build up some statistical significance, and you do that for all the tokens. That can take a while.
And while is end of universe or while is a week?
No, so for Llama, which is not a huge model anymore, it's a 7 billion parameter one, that took a day of runtime on a not fancy laptop. Mm-hmm. So super reasonable. Now, if we were firing these queries at OpenAI, they would probably notice and tell us to pay up. But you could spread that over time. Yeah, you could spread that over time.
I don't know if they would. Like recently, I saw it was so funny. I saw on LinkedIn, it said, for some reason, we got 2 million users registering today all over the world. We are so happy. Our system is popular. I'm like,
maybe not, right?
Or
right.
Or so you just got attacked.
Right. So the point is, as a single user, that's probably a violation of the terms of use. However, yeah, distributed denial of service kind of attack, yeah, maybe that's fine.
But not really denial of service.
Not
They're
really
trying to get your data.
theft
right?
of service.
Theft of service. Yeah.
Theft of service, shall we say. No, that's entirely practical. So the embedding, absolutely, no problem getting that. Theorem says that you can do that. And if you do a little bit of tweaking of the statement of the theorem, you can realize that, oh, I could probably pull out the probabilities of sequences of tokens, which means aspects of the transformer in certain key targeted ways can be extracted in the same way.
Yeah.
So if you want the response of the transformer to part of a query or a certain class of queries, yeah, that probably is something you could pull out in the same way.
Yeah. What I mean basically is like, how about you use it to estimate pre-training. So and it's not even pre-training, it's training, but it's like basically transfer learning kind of, right?
Yeah.
You basically get something. It's not perfect because you were retrieving it, and then you train 10 times faster.
I would say, without a doubt, something like that seems quite possible.
Yeah. So maybe that's what these guys did.
Maybe. I mean, it's unclear, right?
Well, let's hope, because if they really trained the model from scratch for that little money just because of the optimizations they published in a paper.
That seems implausible. That seems implausible. Again, this is basic back of the envelope kind of arithmetic. If we're looking for conditional probability, let's just say 2 tokens. Let's even say 2 words. 50,000 words, say, roughly, 50,000 by 50,000. I mean, that's the number of tokens in GPT-2 is 50,000. So 50,000 by 50,000 matrix. Given this token, what's that token? Okay, so that's 50,000. So that's, 50,000 squared. What? 250 million or something like that?
Yeah.
Okay, great. That's how many entries I need to populate.
Yeah.
And I need a bunch of samples of that. Okay, that tells you how much training data is necessary. Now, what's the size of the context window on these models? A few thousand. So now take that and instead of 50,000 squared, 50,000 to the 2,000. That's a pretty darn big number. That's like heat death of the universe kind of thing. So if you want to estimate the entire transformer, you need that, or you need to know the attention mechanism that was used to limit that down, and you need to know the embedding that was used to limit that down.
Yeah.
This puts substantial bounds on how much compute is necessary. So either that was what they did, somehow found a better way to express natural language grammar across all languages, or they had some help.
I think we can even somewhat see the structure if you look in, the model can be downloaded. So well, the most likely scenario is that
The most likely scenario is they had some help.
that it was the model which was modified.
Yes.
But maybe it would be interesting to run some of your queries on that model.
Sure.
And GPT for, let's say, or whatever version equivalent, and see if there is happens to be like output similarities.
Yeah,
right?
that's exactly the kind of experiment you'd want to run.
Are you going to run it?
That's a good question. I hadn't thought of trying.
Anyway, it would be a proof.
So in fact, one of the things that I mean, this sort of plays out. It's important to recognize if large language models are not general intelligence things, we can do science on them fairly safely. Running controlled experiments of the sort you just explained is a totally reasonable thing to do.
Yeah, it doesn't hurt anyone.
Doesn't hurt anyone. I mean, it consumes electricity, which it can be a problem. But I mean, honestly, one thing that I have not done, but am thinking of actually having students in a class I just proposed as a new course to do, is actually to sit down and run a set of queries against, pick your favorite suite of modern large language models, against Eliza, the original chatbot from the 70s, and just compare and see what the differences are in the output. There's no reason why you can't add DeepSeek to the list or whatnot and run that same sort of story and see if there are similarities or not.
Yeah. Well, I was thinking literally about doing forensics. So basically, since you claim, maybe it's too strong, but since you claim that every training produces completely different embeddings, That's the theorem.
Yeah.
Then if you get the same
embedding.
output for the same
Yes.
embedding, that was the same training, likely.
That is with high probability the same training. Yes, that does follow.
Yeah, maybe Department of Defense should do that
Or something, yes.
Because that would calm down a lot of people. People are really, really worried
Yes.
that if this is true, then we're losing the AI
That's right.
war.
So to speak, yeah. I mean,
Famous,
it's not a difficult experiment to run.
Yeah.
It's not a difficult experiment to run, especially if the model was copied in some fashion. It probably uses a very similar set of tokens. In which case, then we can play the game that we played with Mistral and Lemma.
Mm-hmm.
Use the same tokens, see the output. The coordinates will be different, but the distances between tokens and the dimensions estimated at each token should be similar.
Exactly. Even if there was a little bit of retraining.
Oh, if there was a little bit of retraining, then yeah, maybe some of those tokens are a little different. Mm-hmm. But very, very basically, I mean, again, this comes down to the statistical discipline of rejecting a hypothesis. The hypothesis is, if these two models are really the same, there should be a continuous transformation from one to the other.
Yeah.
Theorem, classic theorem. If I have a homeomorphism, a continuous structure-preserving transformation between spaces, it preserves dimension. Mm-hmm. You can use my dimension estimator to compare.
We should do that. You should do that. This is your paper. You should do that. This would be proving that DeepSeek was copied from specific models would be a big thing.
Sure. I mean, actually, sort of to put a little more academic spin on this, there are open source models that we know their lineage. Mm-hmm. And so if we know their lineage, we can then trace and try to use effectively phylogenetics that comes out of this.
Well, and if it was used on an open model, then there's no problem. It was an open model.
No, well, yeah, but what I'm saying is, let's give ourselves some confidence that this kind of procedure would yield phylogenetics, and then we say, oh, well, we happen to know these are how these models publicly stated were derived from each other, and we can recover that to this level of accuracy. Now, on this not publicly acclaimed model, we see this relationship.
You should apply for funding. Like for this, right? Like now.
Well, yes, now,
because it's kind of an important thing.
Yeah.
Well, yeah, this is wonderful. Is there anything else you wanted to say? We're kind of closing here.
Sure. To close up, let me kind of say the following: when we're doing any of the studies of AI systems, large language models, and whatnot, remember you're dealing with statistical systems. Remember that there are assumptions that were built into them. Develop tests to check those assumptions and to do the scientific process. Build the right hypothesis, be explicit about it, and actually test to see if that rejects. One of the things that was a big frustration in this thus far, which we've overcome, what was the fact that people assumed, hey, it's a manifold. There's even a nice paper written about testing if something is a manifold in the mathematical literature. Problem is that particular paper does not have the constants that are necessary to actually run the test and get p-values. So thinking along the lines that we're doing science with artificial intelligence means that we should be disciplined and use the scientific method.
Mm-hmm. You know, I want to put a catchy title on this talk, this discussion, and I'm thinking, I want it to be catchy but not misleading.
Yes.
So I'm thinking, it will be something like hacking LLMs.
Hacking LLMs. That's legitimate. That's legitimate.
Hacking LLMs, retrieving embeddings.
Yeah. I mean,
second part for the geek guys.
There's an aspect to this that feels like developing a clever exploit for an embedded system. Mm-hmm. So yes. Hacking LLMs.
Very cool. So I hope that we will not find out in 2 weeks that you are working at OpenAI under NDA with just $1 million salary, just not to continue.
That's right.
But it's very, very cool. Thank you very much. This was super interesting. I think we went to many places, but yeah, it was super cool.
My pleasure. Thank you so much.
Thank you.